3.7 practice problems. A 0.2 mole sample of magnesium chloride and a 0.1 mole sample of potassium chloride are dissolved in water and diluted to 500 milliliters. What is the concentration of the chloride inside of the solution? So we are dealing with the chloride only, and this is going to be additive. So there are 2 chlorines inside of the magnesium chloride. And so for every 1 magnesium chloride, there's 2 chlorides. So this is going to be doubled. So I have 0.4 moles of chloride coming from the magnesium chloride. And there is 1 chloride for every 1 potassium chloride. So this is going to stay the same. So 0.1 moles of chloride is coming from here. So adding those together, I get 0.5 moles of chloride. And then the concentration is moles per liter. 500 milliliters is 0.5 liters. 0.5 divided by 0.5 gives me 1. This is a 1 molar solution of chloride specifically because I only care about the chloride ion. A 360 milligram sample of aspirin with a molar mass of 180 grams is dissolved in enough water to produce a 200 milliliter solution. What is the molarity of aspirin in a 50 milliliter sample of this solution? So the molarity is going to stay the same throughout the solution, no matter how much of the solution I have. So I actually don't care about this second part at all. The only part that I care about is how many grams of aspirin's coming in, because that's going to give me the number of moles of aspirin and the total volume of liquid, and that will give me my molarity. So I need to convert 360 milligrams to moles. So there are 1,000 milligrams in a gram. And there are 180 grams in 1 mole. And that will get me the number of moles of the aspirin that was diluted into the solution. Okay, so I ended up with 0.002 moles of the aspirin, and then I have 200 milliliters of the solution, so that is going to be 0.2 liters. So gives me 0.01 molar, or moles per liter. Which is option choice D. A 40 milliliter sample of 0.25 molar potassium hydroxide is added to 60 milliliters of 0.15 molar barium hydroxide. What is the molar concentration of the hydroxide ion in the resulting solution? Assume that the volumes are going to be additive. So what I care about is going to be how many moles of hydroxide are coming from each situation. So I can go ahead and figure that out. The mole ratio between potassium hydroxide and hydroxide is 1:1, so however many moles of potassium hydroxide is in 40 milliliters of that solution is going to be the same as the number of moles of hydroxide. So I can figure out the moles of hydroxide are in 40 mils. And then I'm going to do the same thing for the barium hydroxide, except for there are 2 hydroxides for every 1 barium hydroxide. So I'm going to do the same thing, except for I need to be careful that my ratio is in fact 2 to 1. So okay, this is the number of moles that I have in both solutions, and if I add them together, when I add these together, I end up with 0.028 molar, which is off by a factor of 10 from these answer choices. And I have checked this multiple times, and I do believe that there was an error made in the original writing of this problem, and the answer choice should be C. This is the correct answer, but I believe that when this was typed up, zeros were accidentally left off. A student prepares a solution of 60 grams of glucose with a molar mass of 180.2 grams per mole and enough distilled water to make 250 milliliters of solution. The molarity of the solution should be reported as. So we're going to convert this grams to moles. And then we will be dividing that by 250 mils, so 60 divided by 180.2. And we are going to be dividing that by the 0.25, or 250 milliliters is the same as 0.25 liters, and that gets me 1.332. When I round to 4 sig figs, since I get to report 4 sig figs, since 60.00 has 4 sig figs, and so does 250.0. So you just needed to be careful here that you are reporting to the correct number of sig figs. A student wishes to prepare 2 liters of a 0.1 molar potassium iodate solution with a molecular mass of 214 grams. The proper procedure is to weigh out. So when you are dealing with molarity, you are going to be adding liters of water and grams of the potassium iodate. So we are going to go ahead and get rid of anything that doesn't have us adding liters of water. So this is kilograms of water. This is going to be dependent on the temperature of the room. That will change our density of the water, so that's not going to work out here. Next, we need to figure out how many grams exactly I need to get 0.1 molar. So I'm going to figure out how many grams it is. So 0.1 moles per liter when the molar mass is 214. That's just going to move the decimal over to the left one time, so 21.4 grams. Would be for 1 liter, but I specifically want 2 liters, so that means that I am going to have double the amount, so 42.8 grams of the potassium iodate, again because I need 2 liters of the solution. this initial calculation would give me the molarity if I just want 1 liter, but I want 2 liters. So I'm going to get rid of any of the answer choices that have 21.4 instead, because that is just not enough to make a 2-liter solution of 0.1 molar potassium iodate. Then I am going to check between these two. So this is going to say I'm going to add enough water until my solution has a volume of 2 liters, or I just straight up add 2 liters of water. We are going to add until our total volume of the solution is at 2 liters, because volume is not additive. And we need the total solution to have a volume of 2 liters, and since the potassium iodate is going to take up some amount of space, is going to adjust the total volume. We do need to make sure that the total volume of the solution is 2 liters if I want 2 liters of that solution, because just adding 2 liters is going to not result in exactly a 2-liter solution, since we are also adding powder. Approximately what mass of copper 2 sulfate pentahydride with a molar mass of 250 grams per mole is required to prepare 250 milliliters of a solution of 0.1 molar copper 2 sulfate solution? So I need to figure out how many moles I'm going to need, and then from there I will figure out how many grams. So I'm going to figure out the number of moles that I need for a 250 milliliter solution. 250 milliliters, need to convert that to liters. And then I can use the molarity. And then I can even go further and go ahead and find the number of grams. So we have the molar mass here where we have 250 grams per 1 mole. So 250 milliliters times 0.1 moles times 250 grams divided by 1,000 milliliters gets me 6.25. The closest value is going to be 6.2 here. And again, the question was asking approximately what the value of the mass is, so that is going to be close enough. A student uses visible spectrophotometry to determine the concentration of cobalt 2 chloride in a sample solution. First, the student prepares a set of cobalt 2 chloride solutions of known concentration. Then the student uses a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers and constructs a standard curve. Finally, the student determines the absorbance of the sample of the unknown concentration. The original solution used to make the solutions for the standard curve was prepared by dissolving 2.6 grams of cobalt 2 chloride with a molar mass of 130 grams per mole in enough water to make a 100 milliliter solution. What is the molar concentration of this solution? So basically, this entire first part of the question, I don't care about at all. All it is asking is, hey, what was the concentration of the original standard solution? That's all I'm asking. So I need to figure out my molarity, and I'm going to go ahead and say 2.60 grams per 100 milliliters, and then convert from there. So by molar mass, I have 130 grams per 1 mole, and then I have 1,000 milliliters per 1 liter. And that will get me into the correct units for molarity. Got a little excited with the cancellation there. I accidentally canceled out moles. I didn't mean to. Okay, so 2.6 times 1,000 divided by 100 and 130 gives me 0.2. And I get to have 3 sig figs, so 0.200 is going to be my answer. For an experiment, a student needs 100 milliliters of 0.4220 molar sodium chloride. If the student starts with sodium chloride in distilled water, which of the following pieces of laboratory glassware should the student use to prepare the solution with the greatest level of accuracy? So I specifically want 100 milliliters, and the most accurate piece of glassware is going to be a volumetric flask, specifically trying to get to 100 milliliters. So a 100 milliliter volumetric flask is going to be my best bet for making sure that I have exactly 100 milliliters. How many milliliters of a 10 molar hydrochloric acid solution are required to prepare a 500 milliliter solution of 0.2 molar hydrochloric acid? So this is pulling from the dilution equation. So M1V1 is equal to M2V2. And we are finding the V1 here. So we are going to go ahead and divide the final molarity, which is the 2 molar multiplied by the final volume of 500 milliliters. And we are dividing that by our initial molarity of 10 molar. Since our final answer is also in milliliters, I don't need to worry about changing my volume measurement to a different unit. So 2 times 500 divided by 10 gives me, 2 times 500 divided by 10 gives me 100 milliliters as the volume that I would need. If 200 milliliters of a 0.6 molar magnesium chloride solution is added to 400 milliliters of distilled water, what is the concentration of the magnesium ion in the resulting solution? We're assuming that the volumes are additive. So instead of having 200 milliliters, I now have 600 milliliters, but I need the original number of moles in this original concentration. So I'm going to go ahead and find the moles in that original concentration of 200, that original solution of 200 mils, and there is 1,000 milliliters in a liter. And then we will continue here where we have 0.6 moles per 1 liter. So we'll have 200 times 0.6 divided by 1,000 gives me my initial number of moles at 0.12 moles. Then I am going to divide the number of moles by my volume, which is 600 milliliters or 0.6 liters, which gives me a molarity of 0.2. I get 2 sig figs since the molarity of the initial solution only had 2 sig figs. So answer choice A is my final decision. If 50 milliliters of a 1 molar sodium hydroxide solution is diluted with distilled water to a volume of 2 liters, what is the concentration of the resulting solution? This again is using M1V1 is equal to M2V2. My initial concentration is 1 molar. I'm multiplying that by my initial volume of 50 milliliters, and I am going to be dividing it by my V2. Now you'll notice that these are a mismatch of units, so I do have to choose whether I am going to convert out of milliliters into liters or if I'm going to convert liters to milliliters. So 50 milliliters is 0.05 liters, and I just did that instead of converting the 2 liters to milliliters, but I could have done either. And that is going to give me my M2. So 1 times 0.05 divided by 2 gives me 0.025 molar, and that is my concentration of my final solution. How many moles of sodium ion are in 100 milliliters of a 0.1 molar sodium phosphate solution. So here we need to pay attention. There are 3 sodiums for every 1 sodium phosphate. So I'm going to figure out the moles of sodium specifically in 100 milliliters. Again, out of milliliters into liters, and then out of liters into moles. That specifically is moles of the sodium phosphate. And so I do need to continue down here. For every 1 mole of the sodium phosphate, there are 3 moles of sodium. So 100 times 0.1 times 3 divided by 1,000 gives me 0.03, and I get 3 sig figs, so there should be 2 trailing zeros after that. How many grams of calcium chloride with a molar mass of 111 grams per mole are needed to prepare 100 milliliters of a 0.1 molar chloride solution? So there are 2 chlorides for every 1 calcium chloride, so I do need to be careful there. So I am going to look for my grams of calcium chloride, even though I'm dealing with the moles of chloride. So I do need to be careful here. So I'm looking for grams of calcium chloride are needed for 100 milliliters. My molarity is in liters, so I do need to quickly convert. Then I'm going to convert into moles of chloride. And from moles of chloride, I need to convert into moles of calcium chloride, then grams of calcium chloride. So for every 2 moles of chloride, there is 1 mole of calcium chloride. And then for every 1 mole of calcium chloride, there is 111 grams of calcium chloride. So 100 times 0.1 times 111 divided by 1,002 gives me 0.555 grams of calcium chloride that is needed for that solution. Solid aluminum nitrate is added to distilled water to produce a solution in which the concentration of the nitrate ions is 0.1 molar. What is the concentration of aluminum in this solution? So for every 1 aluminum, there are 3 nitrates. So I just need to divide this by 3, and that will get me my concentration of aluminum, since it is 1/3, or 1/3 of the amount of nitrate. So went ahead and did that. I only get 2 sig figs, so my answer choice is going to be 0.033 molar. The volume of distilled water that should be added to 10 milliliters of 6 molar hydrochloric acid in order to prepare a 0.5 molar hydrochloric acid solution is approximately. So this is looks like a distillation problem. However, this is also going to be a little bit tricky because I want to know how much water I'm adding, not my final volume. So my initial M1V1 is equal to M2V2 is going to give me my final volume rather than my additive volume, how much I need to add to make this happen. So I'm going to have, I get to keep milliliters, so that's nice. So 6 molar times 10 milliliters, and that's going to be divided by 0.5 molar, and that's going to give me my final volume. And I don't want to know my final volume. I want to know how much I need to add. So I want my total volume to equal 120, but I have 10 originally. So 120 minus 10, that's going to give me 110 mils of liquid that I need to add to make that solution possible. The volume of water that must be added to dilute 40 milliliters of 9 molar hydrochloric acid to a concentration of 6 molar is closest to, so again, just like the last problem, I'm going to be using M1V1 is equal to M2V2. However, my answer is going to give me my final volume, not how much water I need to add. So I do need to be careful there. So I do get to keep milliliters again, so that's nice. So 40 times 9 divided by 6. So my total volume is going to be 60 milliliters. However, I need to know how much water I need to add. My initial volume is 40, so 60 minus 40 means that I need to add 20 milliliters in order to dilute that solution to that concentration. What is the molarity of the iodide in the solution that contains 34 grams of strontium iodide with a molar mass of 341 grams in a 1 liter solution? So for every 1 mole of strontium iodide, I have 2 moles of iodide. So I'm going to go ahead and figure that out. So I need the moles of the iodide specifically. I have 34 grams of the strontium iodide, and that is within 1 liter. So that's fine. Converting out of grams, 341 grams per 1 mole. This is still strontium iodide. Then I want to go from moles of strontium iodide to moles of iodide. For every 1 mole of strontium iodide, there is 2 moles of iodide, since there are 2 I's in strontium iodide. Then I can go ahead and plug that into the calculator. So 34 times 2 divided by 341 gives me 0.199. I only get 2 sig figs, so this is going to round to 0.2. Remember that this is moles per liter, so molarity is still the correct unit, and that is my correct answer. When 70 milliliters of a 3 molar sodium carbonate solution is added to 30 milliliters of a 1 molar sodium hydrocarbonate bicarbonate solution, the resulting concentration of sodium is, so I need to know how many moles of sodium is in each of these samples. So I'm going to find that in the first one. So I have 70 mils, get out of mils, and then sodium carbonate. Then added sodium carbonate into sodium. So for every 1 sodium carbonate, there are 2 sodiums. So 70 times 3 times 2 divided by 1,000 gives me moles of sodium. And I'll do the same thing for the sodium bicarbonate. First out of milliliters. Then it's 1 mole of the sodium bicarbonate per liter, and there's 1 sodium for every 1 sodium bicarbonate. So I'll have 30 divided by 1,000. Okay. Adding those together, I get 0.45 moles. And I want to know the molarity, so I need to go ahead and add these together. So this 30 plus 70 is 100 milliliters, otherwise known as 0.1 liters. So 0.45 divided by 0.1 gives me 4.5 molar as my concentration. Which of the following is the best piece of laboratory glassware for preparing 500 milliliters of an aqueous solution of a solid? So anytime that you are going to be creating a solution and you want it to be a very specific concentration, you're always going to use a volumetric flask. Volumetric flasks are the best option every single time, anytime you are going to be making a specific concentration of a solution.